you're looking at the, let's say in the preterm study, you're looking for genes that could somehow explain or predict when this preterm delivery is happening. Do we know at the moment, like what are the what kinds of environmental factors or lifestyle factors or some others that influence this, and how large are the genetic effects likely to be compared to the environmental and other factors?
Yes, several environmental factors are known to affect smoking, of course, alcohol, and all that kind of things. For genetics, the heritable component is maybe 30%, and it involves the maternal and fetal genome, so it's kind of difficult to estimate. But when we do our studies, we rule out pregnancies that involve these risk factors. So they are really pure, spontaneous preterm births. But actually, previous preterm delivery is the most significant predictor of preterm birth. So there really is a genetic component, and we have these large families with multiple preterm deliveries.
To me, it sounds now really that all you need to do is make better models and wait computers to improve. If that's like you can make only semi-good evaluations, or like is it enough that these, or like my first question is that is it really so that this is now what you do the modeling stuff and that's very important, and then like what's the use of these semi-good evaluations? When do you know like when you need to improve it or?
Well, that's a good question. So the problem usually is that, so as to your first question, so we still are not able to solve bigger problems or considerably bigger problems exactly than what we were able to like 30 years ago. And the same conclusion pretty much holds for almost exact solutions. So there really is a need to use good approximations. And the way you usually figure out if an approximation is good enough is that you have a hierarchy of approximations, and you might be able to solve these for small enough systems. So you have some model for your big system, and then in this model system you look at what level am I converged? So at what level is my answer good enough? And then you hope that you will be able to use that level of theory in your big system. And oftentimes this isn't true. So you have to, again, compromise in being able to handle your big system. You might have to use some model that doesn't really give you the right result, even in this model system. So this is something that computational chemists deal with every day. So there is a huge number of different models, and often what people do is they study this model problem, and then they just evaluate a large number of these computational theories, so models, and then they pick the one that gives them the right answer. But the problem is you might get the right answer for the wrong reasons. And then again, it's your expertise that needs to come in and say, oh, but wait, this doesn't make sense. Like, this theory should not give you the right answer here, because you know that this theory is not supposed to work for this problem. So
what was in your last slide? You mentioned that you are working with systems, but you didn't mention what those systems are.
So this what I'm working with are these computational models, and you don't really need to define a system, because the model is supposed to work for anything you throw at it. And so these systems that are challenging for present-day models are ones where this independent particle approximation doesn't really work. And for a lot of these simple systems, the reason why we are able to get really accurate results is that when the independent particle approximation is good enough, then we have a nice hierarchy of stuff we can put on top of it. But when that breaks down, then it's a lot more challenging. And there's basically this hole where I have been developing stuff to fit into. It's very hard to explain in layman's terms what the problem is and like what kind of systems I'm treating, because even if you have thesis in theoretical physics, it takes you a while to get into this problem. So yeah,
I think you did a great job for layman's in your presentation as a whole. So yeah, it was great.
It might be a really stupid question or then a very complex question, but it's been fascinating me for a long time. So I come from media studies and research of digital games, and I never figured out when it comes to these particles that we have in virtual environments, like a Facebook page, email, a dragon in a game, or a character, a hat, anything that you can see in these virtual environments. Can we reduce those virtual elements into physical particles like electrons and atoms in general?
I'm not sure I understand what your question is.
It's a very ontological and perhaps a philosophical question rather than a physical one, but I don't have an answer for this. So I don't know who to ask. Who knows this answer?
Yeah, I'm not sure what the answer is.
So are you asking, is there a way to physically describe a hat on a screen?
Yeah, and of course it doesn't need to be on a screen. So it can also be an digital audio file, or something that is digitally present in a virtual environment. Can we reduce that to physical particles? And if not, what it is then if it's not a physical particle?
Well, this sounds more to me like a maths question. So then you need a representation of some sort. So basically, if you have objects, so let's say you have a hat, a chair, a table, and so on. And then if you can assign numbers, so a hat is 1, a chair is 2, table is 3. Then if you have this kind of a mapping, then of course you can figure out a way to represent it as a physical system. But in the abstract form, it's pretty ill-defined, I'd say.
You showed this graph where you had only this one peak, and I was wondering now that, okay, is this now this like multi-genome stuff? If there's just like one peak, as you said, okay, there's those SNPs above the level, and then you study which genes there are close by. So is it more common to find this kind of one peak and then study it, or that there are multiple peaks and that they are like connecting with each other?
Yeah, compared to international large studies, our sample size is small. That's why we don't have the power to detect many signals. I showed the other Manhattan plot. There are several signals. If you have a sample size that is large enough, you will detect many signals because for a common disease there are many predisposing genes. In our case, we were lucky to find this one peak, so we can concentrate on that. But in reality, there are many predisposing genes.
When you only find this one peak, you don't find all the stuff that is affecting.
Yes.
Yeah, so that's why you need really to have big sample sizes to find the true effects.
And ours is relatively small, so.
So what is small and what is big?
Small is thousands, big is tens or hundreds of thousands.
I guess that depends on the complexity of the disease. The more complex, the larger sample size you need. There are finished diseases where the sample size has been one family.
Yeah, but that's monogenic disease.
That's right.
So,
that's
yeah,
right.
so
But
that's
just so that
different,
it comes back to this exponential growth of the problem.
Yeah, and for complex disease, the effect sizes are really small. So you need a lot of samples to detect.
Is it all in SNPs, or is there another mechanism that might be missing?
Yes, it's not all in SNPs. SNPs are common. There are also rare variants that affect common diseases. They are not caught by GWAS, at least. And there are other mechanisms, epigenetics, that are affected by environmental factors. There are gene-gene interactions that cannot be detected at the moment. So it's not all in SNPs. And the results of GWAS studies don't usually explain all the heritability. They explain a little part. So, and the field is really developing, so I think we will discover new genetic things that will explain more of the heritability.
In both of your presentations, calculations are kind of a bottleneck, and getting power is a bottleneck. And if Minna, in your case, now Finland is building a genome center where theoretically all the babies are going to be sequenced cord blood, which means that we would have one of these days we would have sequence information from all of these. So is the geneticist going to be out of business, and the chemist?
Yeah. I don't know. Hopefully not.
So where is the future in each of your fields? So where do you see it, and how big a part is the kind of the how big a rate limiting step is the computation? You kind of already addressed that partly, but just a little speculation.
Yeah, it is a big step, and for medicine there is the new discipline of bioinformatics. So I don't have the education to do these large analyses. I have learned them by myself. So the bioinformaticists will be doing much of this work in the future, I guess.
Yeah, in chemistry, I believe machine learning techniques are going to be used quite a lot more in the near future. So maybe you can avoid doing these quantum calculations altogether. So we can maybe train a computer to predict these things without actually running the heavy calculations, and then you can do a lot more with less resources. But the thing in chemistry is that if you think about, say, like carbon compounds, there again, the increase in the number of possible ways you can connect the atoms grows exponentially. So the space of possible chemicals is just too big to search through on the computer like thoroughly. So I think you will still need some new ways to sample it, like if we want to develop better drugs and so on. So there's no way we can evaluate all of the possible molecules. So yeah, I think there's still work for people running the computer. So
I think that's also true in the health field, because as Minna said, the genetics, the current genetics, as we understand it, is actually explaining not a lot of even the hereditary part, and there's still the environmental part and the behavioral part as well. So I think that we need still the experimentalist or empirical scientists as well to combine these. So what about if you look at your future? What do you see as the kind of biggest bottlenecks? If you would have all the resources available, what would you see as kind of if you could do whatever you wanted, what would you see the biggest bottlenecks to be?
Getting tenured. Yeah. So currently looking for positions in Europe for reasons you can guess pretty easily.
Although California is a better place than many others on the US currently.
Yeah.
I think the world is open if we have the resources. So I think there will be work for geneticists and bioinformaticists. There will be lots of data to analyze.
How do you see, since we are in this Finnish setting, how do you see Finland as a future option for both of you?
For me, it's fine. I think we have good genetic studies here in Finland.
Possibly.
Okay. Well, thank you very much for both of you and for the lively discussion.